Welcome to STAT 441 at Virginia Commonwealth University. This is the last video lecture for Chapter 3, Probability. In the previous lecture, we discussed what independent events are. So let's review that and then some properties of the independent events. So two events A and B are said to be independent of each other if the occurrence of B does not alter or change the probability of A. So if you look at the conditional probability A given B, then whether B has happened or not has no impact on the probability of A, and the probability still remains the probability of A. So B has no impact on the probability of A. So such events are called independent events. Now, the opposite of this is also true. That means the probability of B given A will be equal to the probability of B. So events A and B are independent of each other. One of the rules that was defined earlier is the multiplicative rule. And in this rule, what we did was we can figure out the probability of A intersection B by using conditional probability. And we had this relation, probability of A given B times probability of B. That gives us the probability of A intersection B. Also, the probability of B given A times probability of A gives us the probability of A intersection B. Now let's see what happens if A and B are independent of each other. So if you look here, A given B is simply A, and B given A is simply probability of B. So we can find the intersection of two events A and B, the probability of intersection of two events A and B by simply finding the product of the individual probabilities of A and B. So this works for independent events because now, as you can see, this part, the conditional probability, it doesn't apply anymore. We just have probability of A times probability of B. So this can be really helpful in finding the probability, solving the probability of intersection of two or more events that are independent of each other. Okay, so let's look at an example and use this rule now to find the probability. So let's say the example that we saw earlier in the die tossing experiment, we showed that events A and B are independent of each other. Event A, if you recall, was observing an even number. So it could be 2, 4, or 6. And event B is observing a number less than or equal to 4. So it could be 1, 2, 3, or 4. And then we've proved that A and B are independent of each other. And recall, we can prove this by showing that probability of A given B is equal to the probability of A. Now, if we needed the probability of the intersection of the two events, that A number is even and it is less than 4, then A intersection B can be calculated simply by multiplying the individual probabilities. Probability of A is 1/2, and then probability of B is 2/3. So multiply that, we have 1/3 as the intersection of the two events. Even if you, and this is a simple example to figure out, even if you looked at the elements that are common to A and B, so 2 and 4 are the common elements, and their probability is 2 out of 6 or 1/3. So that is the same result that we get using the fact that they are independent of each other. Okay, here is in general how we can use the intersection of independent events. So let's say the quality engineer considers the problem of determining whether an assembly line is out of control. Basically, this problem, we need to find the probability that 1, 2, or in general, k items arriving off the assembly line are defective. Okay, so we can generalize this problem by using the fact that each item is independent of each other. Okay, so we can find the probability. Let's start with just 2. So 2 items arriving in succession of the line are defective. Suppose that the line is out of control and that 20% of the items being produced are defective. So for each individual item, the probability of being defective is 0.2, and they are independent of each other. Okay, so let's say D1 is the event that item 1 is defective, and D2 is a similar event for item 2. Both items defective will be the intersection of D1 and D2. In this case, we are assuming that each item is independent of the other, and then we can find the probability that both items are defective. So probability D1 intersection D2 is simply the probability of D1 times the probability of D2. There's a symbol P here. So we have 0.2 and 0.2 for each one, which gives us 0.04 as the probability that both items on the assembly line will be defective. Okay, we can take this idea and we can see this for more than 2 items arriving on the assembly line, and we can generalize it for k items. So let's say we have 3 items, and then we need to find the probability that all the 3 items are defective. So this time we have intersection of D1, D2, and D3. Again, we are assuming independence, so we can simply multiply the individual probabilities. Probability of D1 times probability of D2 times probability of D3, which gives us 0.2 to the third power, 0.008. So it's a very small probability that all the 3 items picked are defective, assuming that there is a 20% chance that each item is defective. We can generalize this for k items. So if we have k items in succession, and then we want to figure out the probability that each of these is defective, then 0.2 raised to k will be, in general, how we can find out the probability that a certain number of items are defective. Okay, now let's look at a couple of counting rules just to figure out the total number of events that occur for a given experiment. So let's say we have k sets of elements. N1 is the first set, N2 in the second set, and Nk in the kth set. And we want to form a sample of k elements by taking one element from each of the k sets. Okay, and these k sets, we're seeing each one has N1, N2 up to Nk items in it, and we want to figure out what are the number of different samples that we can form here. So there's a very simple rule which is called the multiplicative rule, not the same one that we saw for conditional probability, but this is for the counting. So N1 times N2 times N3 and so on. So this is a very simple rule. Let's look at a couple of examples where we can use this rule to figure out the total number of events for an experiment. Okay, so here is the first example. There are 20 candidates for 3 different mechanical engineer positions, E1, E2, and E3. How many different ways could you fill the position? Okay, so in this example, we have 3 sets of elements. So our K is 3. Set 1 is candidates available to fill position E1. Then the remaining candidates are available to fill position E2. And then after filling E1 and E2, the remaining are available to fill E3. So in effect, it's the same set, but we have K the first time, we have all 20. When for the second, we have 19 available. And for the third set, we have 18 available. So what are the total possible ways in which you can fill the position? So using the multiplicative rule that we just saw here, N1 is 20, N2 is 19, and 3 is 18. The number of ways in which the position can be filled is 20 times 19 times 18, which is 6,840 ways. Okay, Let's look at the assembly line example once again and try to figure out how many simple events are possible if we have a certain number of items on the assembly line. Okay, so let's say we are selecting 10 items from the assembly line, and each item can be either defective or non-defective. We Earlier we used this rule. We said the total number of events will be 2 raised to 10 or 1224. Let's use the multiplicative rule to figure out the same number and see if it's the same. Okay, so now since we have 10 items, in our case, K is 10, and each set has 2 items, either defective or non-defective. So each place can be either N or D. So 2 possible outcomes here, and 1 is 2, and 2 is 2, and 3 is 2, so on, and 10 is again 2. So if we multiply all these possible outcomes for each one, we get 2 raised to 10 or 1024, which is the same that we have seen earlier, but it's another way to find this. Okay, similar example, similar idea. Here we have 5 different space flights are scheduled, and each requiring 1 astronaut. Assuming that no astronaut can go on more than one space flight, in how many different ways can 5 of the country's top 100 astronauts be assigned to the 5 space flights? Okay, so let's see how many different ways in which we can assign this. So here we have K is 5. We have 5 flights, and then for the first flight we have 100 astronauts available, so N1 is 100. For the second flight we have 99 available, so N2 is 99, and so on. N3 is 98, N4 is 97, and N5 is 96. So when you multiply these, we get the total number of ways in which an astronaut can be chosen for these. The 5 astronauts can be chosen for these 5 space flights. So it's a huge number. As you can see, it's 9 million plus ways in which we can do that. Okay, now let's look at an example and kind of summarize some of the things that we have seen in this chapter. So here's an example. In a process that manufactures aluminum cans, the probability that a can has a flaw on its side is 0.02. The probability that a can has a flaw on the top is 0.03. So on the side is 2%, on the top is 3%. And the probability that a can has flaw on both the side and the top is 0.01. So 1% chance that the flaw is on both the side and the top. So we can put this in this format. Probability of a flaw on side is 0.02. Probability that the flaw is on top is 0.03. Probability that the flaw is on a side intersection, flaw is on top, is 0.01. Okay, so based on the information that we have, and we can answer a few questions. What is the probability that a randomly chosen can has a flaw? So what are we trying to find here? We are trying to find the probability that the flaw is on his side, on the side union the flaw is on top. So this will be a good case to use the additive rule, because we have the probability on the side, on the top, and then we know the probability of the intersection, flaw on side, intersection, flaw on top. So using the additive rule, we have probability of flaw on side union flaw on top will be 0.02 plus 0.03 minus 0.01. So 0.04 or 4% is the probability that it has a flaw. It could be on side, on top, or both. Okay. What is the probability that it has no flaw? So here we can use the rule of the complement. So probability no flaw will be 1 minus probability that there is a flaw, which is 1 minus 0.04 or 0.96. Okay, another probability that we can find, what is the probability that a can will have a flaw on the side given it has a flaw on the top? So this is a conditional probability. So you can see that given it has a flaw on the top. So we already know that the can has a flaw on the top. Now for the cans that have a flaw on the top, which is 3% of those cans. Now imagine this, we have those 3% cans which have flaw on it on the top. Now what is the probability that it also has a flaw on the side? Okay, so writing it in this format, probability of flaw on side given flaw on top, it will be equal to the probability of flaw on side intersection flaw on top divided by probability of flaw on top, which gives us 0.01 divided by 0.03 or 33%. So basically 33% of the cans which already have a flaw on top will also have a flaw on the side. Okay, here's another example of the microprocessors manufactured by a certain process. 20% are defective. 5 microprocessors are chosen at random. Assume that they function independently. What is the probability that they all work? So we have seen the example where we were trying to figure out that all were defective. Now let's look at the opposite. What is the probability that all of them work? Okay, so we can use the same rule, the intersection of independent events and multiplying the probability, but this time we need to first figure out the probability that they will work. So the probability will be intersection of A1, A2, A3, A4, and A5, where A1 is that the first microprocessor works, second one works, and so on and so forth. We can multiply the individual probabilities. It will work, each one will work with a probability of 1 minus 0.2 or 0.8 raised to the 5th power, which is 0.328. So that gives us the probability that all the 5 are working. Okay, so that's all for this chapter. Thanks for watching, and please watch the next video for discrete distributions. Thank you.